So a lot of people ask about Newton's method and the math behind that in order to understand it. So I wanted to explain a little bit about what you're doing with Newton's method. Let's imagine that we're trying to find the roots of the quadratic equation. Let's see. We'll solve f of x is x squared minus 1, the example problem I've got. So let's draw our chart here. We're going to have a quadratic curve. Actually, I'm going to scale things a little bit. So normally we would represent this as, all right, at the value of x is 0, then it is -1. And that at value of x is 1, then f of x is 0. And then at x is 2, then f of x would be 3, right, up here. And then it'll be symmetric on the other side. But actually, I'm going to draw this a little bit skewed just to help us visualize what's going on with the algorithm a little better. So let's draw it way out of scale. Here's our horizontal axis again. Here's our vertical axis. And I'm going to draw it like this. That'll just help us visualize things a little bit better. So pretend this is y is -1, this is going to be x is 1, and this is going to be x is 2, and then x is 3 is somewhere beyond here. Okay, so we want to find this root here. And so we're going to start out with an initial guess. We're going to say x naught is 0. That is where we're going to guess the solution is. So we're going to say, all right, I'm going to guess, excuse me, x naught is 2, let's say. I'm going to guess that this is the solution. This is where the function actually is at x is 2. The function is not at 0 where we want it to be. We want to find x is 1, but we don't know that yet. We just have our guess. We're going to guess that it's at x is 2. It's wrong, so we check our guess. We say, what is f of x naught? F of x naught is 3. 2 squared minus 1 is 3. Okay. How do we solve this? Well, we can't solve this quadratic equation exactly. Well, we can actually. But let's pretend this is a more complicated function. We don't know the quadratic formula or something like that. But let's say we do know how to solve linear equations. And let's pretend that this equation is linear. I mean, at least locally, that's a reasonable approximation. If you zoom in really close to here, you know, for any function that's reasonably well behaved, even if it's very squiggly on the outside, but if you zoom in really, really close, this is basically just a straight line, you know? Zoom in really close to this little box here. It's just a straight line there. Zoom in really close. So we can imagine, let's say that the function were just a straight line, what would it look like? It would look like the tangent line. That's the line that intersects the curve at just one point. And that's what it looks like. And if we know what that line is, and we find out where that intersects the x-axis, maybe that gets us closer to where the quadratic curve intersects the x-axis. Okay, so the idea is we are going to approximate this quadratic curve as a line, as a straight line, that is tangent at that point. We're going to approximate the quadratic curve as the tangent line. We're going to follow that tangent line back to 0, back to x, the x-axis, or y equals 0. And we're going to say that's going to be our new guess. We're going to say here is our initial guess. Our new guess is where the tangent line hits. So this is going to be our x1. We want to get there. How do we get that? How do we know what that is? Well, one thing we do know is we know how high up we are to our existing point. We know that the tangent line, what's the slope of the tangent line? The tangent line has a slope of f prime of x naught. Let's see. And in this case, f prime of x is 2x. Okay. What is the definition of, well, it's not the definition of a derivative, but what does a derivative mean? It's the slope of the line, you know, right? And what is slope? It's rise over run. this is the rise, this is the run. So let's call this delta. Delta is the difference between x1 and x0. So delta is x0 minus x1. That's the run, and the rise is f of x. The rise over the run must be equal to the derivative. So we can write out that as an equation. We can say the rise, f of x, over the run, delta, is equal to f prime of x0. Well, we know f prime of x0, we know f of x0. We're trying to find delta. If we know delta, then we know the difference between x0 and x1, so we can figure out how to get to x1. So delta then is f of x0 over f prime of x0. Let's call this delta naught because it involves x0. Okay, so from there we can say, well, x1 then is x0 minus delta naught. We can calculate the new guess. So in this case, delta naught is, let's plug in the numbers. F of x0 is 2, and f prime of x0 is 4. Excuse me. F of x0 is 3, f prime of x0 is 4. So delta is 3/4. x0 is 2 minus 3/4, so that's going to be 1 3/4 or 5/4. That completes the first step of our iteration for Newton's method. We've taken the tangent line, we've written it back down to the x-axis, and now we're going to say, all right, here's our new guess for the solution. Is it correct? We're going to start over from the beginning again. Basically, x1 becomes our new x0. Or you can start naming successive guesses with successive numbers. So we can say, what is f of x1? It's up here. Is that less than or equal to our tolerance? Is that close enough to 0? Let's visualize epsilon as this here. We're only interested in a guess such that the value of f at that guess is within epsilon of the x-axis. So is it? No, it's not. We have to continue with our iteration. So what we do is we find out what is the slope at this point, and we're going to solve the same equations that we did for x0, and we're going to find out, well, this is our delta 1, the distance between this x1 and some new x2 guess. So we're going to find out where the tangent line intersects the x-axis, and we're going to say, all right, well, the guess is now x2. Is f at x2 less than our epsilon? No, it's not, so we have to follow the new tangent line. It gets us to here, which we'll call x3. At x3, does the function value, is that less than epsilon? Is the absolute value of the function, I should say, is that less than epsilon? Is it within these bars here? Yeah, it is. So close enough, as the smaller and smaller we make epsilon, then the closer and closer that we're going to get to our actual answer, because we're going to satisfy the function value equaling 0 much more closely. And so Newton's method is an iterative way. We approximate whatever curve it is, quadratic, cubic, it could be the sine function, it could be a logarithmic function, it could be a combination of any of those. Under certain conditions, it's going to work even for more complex curves, not just the quadratic curve. We already know the quadratic formula, so we don't need Newton's method. But it actually works for much more complicated things. I just gave the quadratic function because I knew that was going to work well for that. Newton's method is not guaranteed to work. What's another downside of Newton's method? Well, you don't get both roots, right? It's only converging to this root. X is equal to 1. What about the other one on the other side? From the quadratic formula, you know that there's got to be another root. But Newton's method only gives you 1. But because it works in more general cases where we don't have a formula, Newton's method is extremely powerful. So it's very general and very helpful. Again, it doesn't always work. Some people might ask, Well, what if you started here? Well, what if you started there? If that was your guess, x is 0, well, the tangent line never intersects the x-axis, so it's going to fail. I didn't say Newton's method was guaranteed to work. It will give you at most one root. It might fail, but it can work, and that's what we're after. And so that's why we do this assignment. It's a good application of the Java that you know so far. You're seeing that it's very similar to C++, and it could be very useful in your next math assignment, solving an equation that you've never seen before, at least numerically.